Hi and welcome to video 1 on this video series on Financial Mathematics, Unit 4, Topic 1 of the General Mathematics course. So there's your learning goal, and in this particular video we're going to just review our knowledge on recurrence relations. So a recurrence relation is a rule that defines the value of a term based on the value of a previous term. So we get this recurring forward sort of process here. So let's have a look at some examples. You might write that the next term is equal to the previous term times 2 plus 7. So then we get this pattern occurring here. If the first term was 6, then term 2 was the previous term, 6, times 2 plus 7, which is 12, plus 7, which is 19. Term 3 is the previous term, which is 19, times 2, which is 38, plus 7, which is 45. Term 4 would be 45 times 2 plus 7, which would be 97, so on and so forth. That's how a recurrence relation works. It links two consecutive terms and tells you the value of the next term based on the value of the previous term. It can also be written, and I say also be written, this is a common notation, as Tn plus 1 is equal to Tn times 2 plus 7. So we've got the same rule occurring here. Next term equals previous term times 2 plus 7. But it's just written mathematically. Tn plus 1 is saying term n plus 1. Now that sounds complex, but that n plus 1 just represents a number, and it's equal to term n, which is the previous term, because n plus 1 is 1 on from n. So there's a relationship between those two terms. Let's look at an example. A recurrence relation has the rule start with 7, add 5. Write down the recurrence relation. So I'm going to do this using the technical vocabulary, and that would be Tn plus 1 is equal to the previous term, Tn plus 5. So that's what this means. Now, this is defining our first term, term 0, or term 1, depending on how we're going to set up our function. And it doesn't really matter because it's just the linking of terms. And this is our rule, and that rule relates directly to what happens to Tn to get us to Tn plus 1. Determine term 4. So I'm going to say term 1 is equal to 7. That's our standard form for this. It's just that term 0 notation here will come up a little bit when we get into our compound interest and simple interest forms here. Term 2 is equal to term 1 plus 5, and that's obviously equal to 12. And term 3 is equal to term 2 plus 5, which is 12 plus 5, 17. And term 4 is equal to 17 plus 5, which is 22. So the fourth term, or term 4, is 22. And now time for some light-hearted entertainment.
Why did the little cookie cry? She was feeling crummy.
Let's look at a second example. Given that Tn plus 1 equals 3 times Tn minus 2, determine the next 5 terms if term 1 is equal to 7. So, if term 1 equals 7, we want the next 5 terms. And I'm doing this horizontally, which is a little bit of a no-no, but it's the easiest way for me to fit this on the page appropriately. Term 2 is 3 times term 1, which is 7, minus 2. That's equal to 21 minus 2, which is 19. Term 3 is equal to 3 times 19 minus 2, 57 minus 2, which is 55. This is going to quickly get out of hand. Term 4 is 3 times 55 minus 2, which is 165 minus 2, 163. Term 5 is 3 times 163 minus 2, which is 489 minus 2, 487. And term 6, the fifth of our additional terms, is 3 times 487 minus 2, and that's equal to 1461 minus 2, which is 1459. And I might just check that quickly. That's 3 times 487 minus 2 is 1459. Good. And so there are our subsequent 5 terms as requested. Don't confuse the next 5 terms with including T1, because that's not asked to be included. Bonus multiple choice. Which option below is also a correct equivalent recurrence relation? I've written this question deliberately to point out something. This Tn, well, this means that, let's say that's T7. Well, 3 times T7 minus 2, well, that's equal to T8. And if that was T14, well, this would be T15. If that was T100, this would be T101. There's a connection between consecutive terms, and on the left-hand side is the upper of those two consecutive terms, and inside the function is the lower. So that's a relationship. Now, we're using Tn and Tn plus 1, but there are some places that might use Tn here, 3 times something minus 2, and this would be Tn minus 1. So this is Tn and Tn plus 1. Doesn't quite work, although it's close to a rearrangement, and you could test that. This is Tn plus 1, and this is Tn, so it's the same function as before. We've got a plus here, so that's completely different. Tn and Tn minus 1 with the 3 and the minus 2. So C is the answer here. C is the same. We've still got Tn is the next term, where Tn minus 1 is the previous term. And we've still got times 3 minus 2. So there are some variable notations that you might see, so just be wary of that. Now let's look at something that might be a complex unfamiliar question. It's not too hard, but it does rely on a bit of algebraic nous, I suppose. So we're told that Tn plus 1 equals Tn squared minus 1. But in this case, we're given T4 and we need to find T1. So this function takes us from a lower term to an upper term. How can we rewrite this so that we're now going from an upper term to a lower term? What I'm going to do is I'm going to rearrange this. So I'll get Tn plus 1 like that equals Tn squared. And then this means, therefore, I'm going to swap sides as well. Tn is equal to the square root of Tn plus 1 plus 1. And so this is telling me that if you know the upper term, you can find the term below it. So if you know term 10, you can find term 9. If you know term 9, you can find term 8. Certainly, if you know term 4, you can find term 3 to find term 2 to find term 1, and you've solved the problem. So let's go through this process now. Term 3 is equal to the square root of term 4, which is 63 plus 1. And 63 plus 1 is 64. The square root of 64 is equal to 8. Term 2 is equal to the square root of 8 plus 1. And 8 plus 1 is 9. The square root of 9 is 3. And term 3 is equal to the square root of 3 plus 1. And that's equal to the square root of 4, which is 2. And sorry, that should be term 1. We're going down, aren't we? Not up. So term 3, term 2, term 1, and term 1 is 2. So there we've applied our backwards design to determine the value of term 3, term 2, term 1, which is addressing our question. And that was a complex question, possibly unfamiliar. Now you can be a little bit calculator clever, although it looks a little bit like I've written being calculator diva. But calculator clever. We can use our answer key. Now I don't have the calculator on the screen, and I can't do that at this present point in time, but I'm going to describe it to you, and I've shown you the keys in pink there. So if we use the answer key, we can do a recurrence relation really easy. And if we start by describing A0 or T1 or wherever we're starting with, in this case I've said 7.2, I type in 7.2, it's the first term, and then press equals. And so I've typed in 7.2 and pressed equals. And now I'm going to use the answer key to write the next step of my recurrence relation. So I'll do answer times 2 equals, and it will give me 14.4, but this is where the magic starts. If I press equals again, it does the whole calculation again for me, giving me 28.8, and equals again 57.6, so on and so forth, and you can see it growing. So we can put in the recurrence relation straight into our calculator as many times as we need to, but of course you need to make sure you don't forget to count. So there is the can you component of this lesson, and of course the reference to the textbook exercise. Have a look at that. Do your best, answer questions of your teacher if you have any. All the best.